Back in the good old days, you only had one CPU, which means it could do one thing at a time. And they created the illusion of doing more than one thing at a time by switching faster than a human could react. So that you get a slice and you get a slice and you get a slice, they in fact called it time slices. So you do have more than one program running on a CPU, but only one at a time. Then they came up with the concept of a thread. A thread is just a program within a program. So really nowadays everything is threads. It's just heavyweight and lightweight threads. If you have multiple CPUs or multiple CPU cores, they all can be doing something at the same time. And there are issues with that. Thankfully, multi-threaded programming is actually very easy. You just have to be careful. It used to be the Wild West, but now you've got languages like C# with built-in primitives and beautiful features. And if you actually use them, it's incredibly easy. But you can easily forget and make a mistake. The basic architecture, let's have a CPU. So we've got two cores. We've got a CPU. Don't worry about hyper-threading or symmetric multiprocessing or whatever. That's not relevant here. Just think about actual cores. CPUs have a cache. Each CPU has its own cache. It's just memory, because RAM is slow, especially if you have more than one thing competing for the memory controller. So if you have a CPU that's working on a small subset of data, and it can keep fetching that, reading and writing to its own cache, then that's a great savings. If this program is running and this program is running and they don't interact in any way, this one barely needs to write values out to the memory. It can just say, yo, memory controller, whenever you get a second, come grab this. Otherwise, don't worry about it. So if something else is doing heavy writes to main memory, it can do that. But you can obviously see if there's two different snapshots of memory that the CPUs are using that's not actually memory, you can immediately see there's a problem. Here's the memory controller. It's just the thing that manages memory. You can request a read and a write. And then you have memory, RAM. So that's the basic architecture. RAM is the thing. Through the memory controller, CPUs can request reads and writes, and they keep them in their cache when possible. You have a thread. Here's a thread. It's got memory. I'm going to put it in quotes. Quote, memory. And over here, quote, CPU. The thread can be put on this CPU, it can be put to sleep, it can be put on this CPU. It can have its RAM here, or all three at once. The operating system, the CPU, all of that manages it. From the point of view of the programmer, you see memory, and it's all yours. And you have a CPU, and it's all yours, and you're always running no matter what. And the illusion comes because whenever the CPU decides you get to stop running, it just takes a snapshot, like a save state in an emulator. It saves whatever was going on, puts you away, does something else, puts you back, and you have no idea. So you can imagine this memory just overlaid, CPU overlaid, and you don't ever have to worry about any of this. It's all done automatically. You just have to worry about this until there's something else to worry about. The first thing I'm going to mention is actually something you don't have to worry about. It's something you used to have to worry about, which means it's going to come up if you're looking for this information. Also, if you're trying to, let's say you're doing a hobby project and you want to create your own, multi-core CPU, you can do it. You grab a couple microcontrollers, hook them together, you got multiple CPUs. And you're going to run into these issues because they're not going to be these fancy new Intel and AMD CPUs with advanced architectures, so you still need to know this. It's something called cache coherency. This CPU is running a thread that requests a value from RAM. It gets put in its cache. This CPU is running another thread, let's say from the same program even, requests the same value from its cache. This CPU changes it in its cache. This CPU is still using the old value. Now we got a problem. Modern, and I'm speaking desktop and laptop. I don't know about mobile phones. I don't know about the 2-in-1 nonsense. But normal computers, desktop and laptop, normal computers, x86, x64, 32, 64-bit modern architectures you're going to find on every normal computer you encounter, uses cache invalidation. When this CPU changes the value of a variable in its cache, the memory controller is immediately notified with no delay, no problems at all. The memory controller immediately knows. And the second that this CPU tries to say, give me this memory that's in my cache, the memory controller sees that as well, and it says, no, that's old, you have to do it the slow way. If the cache has not been invalidated, it can still use its value. But modern architectures account for this, and there is overhead, but it's more important that it works. So modern architectures will automatically manage the cache so that there's never any outdated values whatsoever. You cannot worry about it. But if you make your own, if you're doing a hobby project, if you're using some extremely old hardware, well over a decade, I think. I don't know the exact number, so let me not say that, but I believe it's over a decade. It could be a problem. Thankfully, nowadays it's not, so you can just not worry about that. Now to the things that still are problems. Modern CPUs have a whole bunch of things in them, and they can do multiple things at the same time, even inside a CPU, because a CPU's got, the integer unit and the float unit and this unit and that unit, and there's no reason why it couldn't be using all those units at the same time. So when a CPU nowadays receives a list of instructions to execute, it puts them in little buckets. And every time, it's one bucket per unit. So every time the integer unit can do something, it'll pull from the integer bucket. And every time the logic comparison jump unit can do something, it'll pull from that bucket. And the bucket is programmed to say, okay, like this is an add instruction. Are both of the things I'm adding already loaded? If no, then it sits there and waits. So it won't let the CPU take it from the bucket. But as soon as both things are loaded in memory or registers or whatever, it'll say, okay, you can have this. So the CPU is just constantly trying to take from buckets every time it has, free brain space. And thus, it can do things out of order. It can do the instructions in a different order than you wrote it, than the compiler wrote it. But it's always a guaranteed accuracy. It's not going to just reorder however it wants and give you the wrong answer. Whenever it reorders, it has to make sure that the reordering doesn't have any problems. Like if you add to one variable and add to another variable, and they're not interacting, you're just adding to two different variables. Well, that's a bad example because it's both the integer unit, but you get the idea. You could read from memory and you could do this. And you can do those in any order, and it's not going to matter. So it guarantees correctness within the thread. Within your little thread model, where you have one CPU and one memory and it never changes, and you never stop running, it guarantees correctness no matter what it does. However, when you are doing more than one thread at once, it cannot guarantee correctness because it does not know. It's not an intelligent entity, and it knows about the thread model. It doesn't know about multi-thread models because that's impossible. That would mean the entire program on the computer, every application, everything, is one program. That's not how it works. It knows about threads, and it guarantees threads. Imagine you have the following. A equals B plus C. D equals E plus F. Ready equals true. This is what's called the producer and consumer model. One thread creates something, the other thread uses it. This is extremely common. Obviously, this is a stupid example. This is for illustration. You get it. But from the CPU standpoint, it can certainly do this. Just looking at this, there's absolutely no difference in these two things. Ready, D, A, none of these interact in any way. What happened, though, is it requested E and F from memory so it could put them in D, but there was a delay. Some other program had charge of the memory controller right that second, and it had to wait a moment. So it said, in the meantime, well, I can write to memory. I'll just write ready to true, and it's just putting it in its cache, and invalidating that cache line, of course. But it doesn't need to take up the valuable memory controller's time any more than that, so it can do the ready equals true, and then in the meantime, the E has finally come in, and it can do that. And from a thread model, this is guaranteed correct. There's no reason it can't do that. And a lot of the time, this is great because it's much faster. But then you have other code. Another thread in your program. Wow. Not ready. Wait. So it sits there, waiting, checking ready. Ready's false. Oh, ready's true. Now, G equals A plus D. This is another thread in your program. This is now consuming what this one produced. Except, this happens after ready equals true while it's still waiting for E, so D hasn't been changed yet. D is wrong, and thus G is wrong. That's what happens. It's commonly called CPU instruction reordering, but it's not just instructions. It's memory accesses. Other things than the instructions could be in the same order, could be executed in the same order, but the reads and writes may be in a different order. As long as per thread it's correct. As long as per thread it's correct, they can happen in different orders. So how do you solve this? On an assembly language level, there are commands you give to the CPU to specifically instruct it where it is and is not safe to do this. Your programming language, your compiler, automatically inserts these where you use synchronization commands. Usually, and I'll get to this in a moment because the compiler can do things too, but there is a command in C# in the thread class called memory barrier. It's basically a wall. you put up this wall, and you can say A equals over here, and D equals over here, and ready equals over here. So you put up this wall, and the CPU could reorder these, but it can't reorder this, and it can't put this over here. It cannot cross the wall. So it's nice and easy. You could do a whole bunch of stuff and let the CPU and let the compiler optimize it however it wants and make it as fast as possible, and then you put up a wall, and after the other side of the wall, you just say ready equals true. That's how you do a producer-consumer, is you do all your stuff and let it optimize and let it be fast, and then when it's all finalized, you put up this wall, which means everything on the left side of the wall has been 100% completed, and everything on the right side of the wall is 0% completed, and then as soon as you cross the wall, it'll do the ready. So that's the CPU. The compiler can do it too. So a CPU has something called registers. You know what a register is? It's just some latches or flip-flops. They're actually in the CPU. The CPU is not a giant combinatorial thing with 8 million pins inputs. It has registers, 64 bits, 64 bits, 64 bits. There's no way you could do that. You'd have a kabillion pins. So you have to load and store into registers and then do operations on those registers. So you'd have 2 add registers, and then the add operation is connected to the add registers, and then there's an output register. This is not how modern ones work, but this is how you might implement your own if you're making your own CPU. So you'd load values into the registers, issue the add command, read from the output register kind of thing. So let's say at a particular point in your program, your compiler knows there are 4 registers available that are just free, that cost nothing. If it wants to use more, then it has to store something in slower, like the stack or something. It has to store it in slower memory. So let's say you have these instructions. Start equals clock. Clock is a function that gives you the time of the day. Then you call a function, func. You call it with A, B, C, and D. These are variables in memory. Then you say end equals clock, and time equals end minus start. This is called profiling or a stopwatch. You look at the clock, you do something, you look at the clock again, and you see how much time elapsed. And this is how you can tell how much time func takes to run. A very simplistic example. Here's the thing though. Let's say that clock simply reads a CPU register. Let's say the CPU has its own clock and you just read that clock. You just read the clock. Well, cool. But here's the thing. You read the clock and you store it in start. That takes a register, so now you got 3 registers available. But then you got to load A, B, C, and D to call func. Well, now you're going to have to store start somewhere, so you have 4 registers again, so you can load A, B, C, D and call func. And then you have to restore it, and that's slow. Why not just put this here? Well, obviously we can see why not, because that breaks it. But what if the compiler doesn't know that? Because the compiler knows that clock has no side effects. You're reading a register. It doesn't change the system in any way. It doesn't change any other code in any way. It's just there's a register, you read it in. And it's a read-only register. Nothing else can be writing it. Nothing else can be doing anything with it. You just read it. So why not? And so it does. This is a real example, by the way. I Googled this to try and find a real example because I didn't just want to make crap up. This is a real example somebody gave, that their code did this. And this is exactly why, because it was reading a hardware register. So the compiler loads A, B, C, and D with the 4 registers, calls func, and then it calls clock. But that's right before end, so your start and end is practically the same time, and time is 0. So in other words, the code that the compiler generates is as follows. Func A, B, C, D, time, because start and end were just temporary variables. We care about the time, not the literal start and end time. All we care about is the elapsed time. So time was stored in RAM, start and end weren't. Time equals clock minus clock. This is what it optimizes to, because it knows that start and end aren't used anywhere, so why does it even need that variable? You know, it'll do registers, whatever. It'll probably call clock and have 2 registers and then issue the subtraction command, so they'll still be separate, but, fundamentally start and end don't even need to exist from a code standpoint. You could write it like this, and it would just allocate registers. So this is what happens, and that's why it breaks. So once again, there are constructs in languages that tell the compiler to not do this. So you can use those constructs. You could use a memory barrier, but that's slow, because the compiler is the one allocating registers. The CPU is not going to reorder it this way. The CPU is not going to do this. The CPU is reordering memory accesses. Actually reordering commands is not going to do it. So only the compiler is doing this. So you want to use just a compiler instruction. So you could specify this function has side effects or whatever, don't reorder. Also, if this clock command, if this clock function was a system call, if it was actually part of the operating system, the compiler would not do this because it operates on a better safe than sorry, because you don't want to have wrong code. You optimize when you know it's safe and otherwise don't touch it. Let the programmer worry about it. So if clock was a system call, the compiler wouldn't know what in the blazes it does. It could cause fireworks to erupt for all it knows, so it had better not do anything with it. So your code would work perfectly fine. It would never do this. But it knows it's reading a read-only CPU register whenever you call clock. There's no side effects there. It can do this, unless you tell it not to. Now you might say, why would you ever want it to do this? Why in the world would this even be a feature? Because 99.999% of the time this is fine. Because it's not going to take this and put it 6 functions down. This is going to reorder it in a very small space. It's only going to reorder it a little bit, for whatever registers it has available or whatever's going on. So it's only going to be a small thing. So usually what happens is somebody just wants to timestamp something or get an idea of like I want to update my display, my progress bar once per second. So every time I do something, I check the time. If it's been a second, update the display, for example. 99% of the time, this doesn't matter. So it's fair for the edge cases, we call them edge cases, it's fair to say, okay, there you have to use a command. So what usually you're supposed to do is you use a standard library that has a stopwatch command, a stopwatch class or function. And in the stopwatch, they thought of this and they've got the thing in there. So if you use the stopwatch function that's built in, then this is already done for you and it's going to work. This is if you do it yourself and it's a gotcha. Because nothing's going to tell you this happened until your stuff doesn't work. But now to the meat and potatoes of multi-threaded programming. Actually, the code you write and concurrent access. This is where you have a list of fruit and you have 2 different threads trying to access the list of fruit at the same time. This is what people normally think of when they think of multi-threaded programming. And the reason for that is you have to use the tools properly. If you always use the standard library function stopwatch instead of trying to create your own. If you always use the language built-in synchronization functions instead of trying to get funky or get crafty, clever, if you just do it the right way and you're very careful, none of this ever happens because those instructions take care of everything for you. It's like a white padded box clean room, but it's slower, which is why people try to take shortcuts. They try to do things like lockless code. We'll get into that in the future. And it's good. Lockless code is great. It's nice and fast, but you gotta know what you're doing. Concurrent access. This is the real problem that programmers have to solve. Here's an example. A equals A plus 1. What happens if you're doing this? Let's say you are accumulating how many times you've done something. Well, if you've done it 3 times, add 1, 4. But you have to read it first. You have to read A, it's 3, then add 1, then write it back. What if A changed? So register 1, A. Register 2, 1. Register 1 gets register 1 plus register 2, and A gets the value of register 1 back. That might be your machine code. What if A changes? Because you've got another thread doing A equals A plus 1 at the same time. If you're processing 1,000 items, why not spin off 2 threads and each do 500? And then they keep track of how many they've done, that's why. So you've got something called an atomic operation. Atomic, and the word means cannot be split, which is why they named the atom for that, and then of course we split it. But the word means it's one piece, it cannot be split. So the CPU has a special instruction, several special instructions for common things like that, where you can read, compare, and modify, or whatever combination of very primitive things, and the CPU guarantees it's all in one single clock cycle, or not clock cycle, but like one single pass, so it cannot be interrupted. So that's a thing, and your language is going to give you ways to use use those. But there's something even easier. I've mentioned modern architectures, desktop and laptop computers. I don't know about phones or tablets, but desktops and laptops, 32 and 64-bit Intel architecture, so that's Intel and AMD, modern Macs, modern PCs, anything running GNU Linux, mostly. What you think of right now as a computer. You know how I talked about the cache coherency guarantee? There's another guarantee. All aligned reads and writes of anything a word or shorter is atomic by default. What does this mean? What is a word? Well, you've got bytes. This is 1 byte. A 32-bit machine, a byte is 8 bits, so that's 4 bytes. So 4 bytes is a word. What does aligned mean? It's just where it's placed in memory. I'm going to skip that for now. We'll do that in the future. But if you're not doing anything special, it's going to be aligned. Let's just say that. If you're not using any fancy override constructs, if you're just writing a program and not doing anything weird that you have to know what you're doing to even do, it'll be aligned. Everything just auto-aligns nowadays. So it'll be aligned. And then anything that's 32 bits or less on a 32-bit machine. Anything that's 64 bits or less on a 64-bit machine. So an int, a bool, a char, a short, a pointer, or a reference. That's the big one. So this is a big one in lockless programming. Let's say you have code that creates an object, and it starts like object equals null. And then you create the object, and then you say object equals thing I just created. So up until this instant, object has been null. And then you create, you don't change object. You're using a temporary variable or whatever. You're doing all this computation. And then you set object equals the final value as the very last thing you do. Now this can be reordered, so you have to remember your memory barrier, because you don't want to set object to the value before you have the thing, because you could have this value. The compiler might have this pointer before the construction code has finished running, depending on how it's programmed, because the compiler does whatever it does. So you do a memory barrier and then you set it. This is the same as saying ready equals true, because some other code could be checking object null, wait, object null, wait. Oh, object's not null. And it just read it and used it. But because a pointer or a reference is always the word size, it's 32 bits or it's 64 bits. That's how big a pointer is. To say, there's my object, it's right there. It's guaranteed, it'll be aligned, and it's guaranteed atomic, which means you read it and the whole thing was there. You know, if you have a 32-bit machine writing a 64-bit value, it's going to be in 2 32-bit pieces. It's going to write one, it's going to write the other, and the other one could start using that before you're done. But on a 64-bit machine, it's one 64-bit piece. So that whole thing, bam, all at once. So there's fancy, simple lockless programming you can do because of that guarantee. But that's when you're doing something very small, like setting a reference that you just filled. What if we have a list? We have a list. Start. This is just a container to say where is the first item. We got A, we got B, and we got C. This is a list that has A, B, and C in it, and start just tells you where the list starts. Cool. Each one points to the next one. This is called a linked list. What if you have code that says X next equals start next, and start next equals X? We're inserting X. X is going to point to A because that's start. That's what start is pointing to. So X points to what start's pointing to, and then start changes to pointing to X. So it'll be X, A, B, C. But then you've got another thread. Y next equals start next. Start next equals Y. This code just inserts Y at the head of the list. So what we want is X, Y, A, B, C, or Y, X, A, B, C. I guess we don't care which is first. But here's the thing. What if we do it this way? The CPU runs this command. Oops. It has decided, the operating system has decided now it's this thread's turn. So now this runs, and then this runs, and now it's done. Switch back to the first one, this one runs. That's perfectly valid, that's what it does. It switches between threads so they all have the illusion of happening at the same time. But what actually happens? Well, here's X, and here's Y. X next equals start next. So X points to A, but then we switch threads. Now, Y next equals start next. So Y points to A, cool. And then we say start next equals Y. So now the list starts with y. So now start is pointing at y. But then we switch back to here and we say start next equals x. So now start is pointing at x. So our new list is start, x, a, b, c. Y was created, y was added to the list, and it's gone. It's disappeared. It got taken by a Langolier. This is where you use synchronization. In C#, my favorite language, it's not perfect, but it's my favorite language. It's so easy. A function you can just say synchronized, or you can just say lock, and put code in a lock. And what happens is, basically, when this code is running, it's going to tell the list, listen, I'm going to be modifying you. If somebody else tries to modify you, tell them to wait, because it's not going to work if we try to do it at the same time. So X acquires a lock on this list, and then it starts working, this other code starts to run, and it tries to acquire a lock on the list. And it says, oops, can't do that. It's already locked. So what happens is this thread immediately yields. It could do something else if it's programmed that way, but it's not. It needs to update this list. So it says, wait on the lock. So it gets in line. The lock has a list of people waiting on this lock. And so it immediately gives the CPU up, which is going to switch back to here. This is going to do its other thing and release the lock. And then the lock is going to say, oh, somebody's in line, and it's going to immediately switch over to them, or not. It can be programmed different ways, but the default behavior is likely going to be that. Either this one is going to run for a little bit longer, and then this one's going to be next in line, or it might switch immediately. It depends on the language, and you can probably change it. Some locks might even have a command. When you release the lock, you could explicitly say, if anybody's waiting, go to them right now. But that's the basic concept, and that's all you ever need. If you pepper your code with these every time you're doing something multi-threaded, if you pepper your code with locks, it'll be fine. And locks, at least in modern languages such as C#, are not that slow. They are comparatively slow. If you have locks everywhere, even if you're not contending, that's the big thing. If somebody's got something locked and somebody else is trying to get in, that's where the slowness comes in, because this one's waiting and there's context switches and all this. But if you lock something and release it and nobody ever wanted it, and it was good luck, then it's not that slow. So yeah, be safe. And if you're safe and careful, you never need to worry about anything. Don't do lockless programming. Don't do fancy stuff. Just use locks and use normal code, and you will never, ever, 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 ever have a problem. But what's important is realizing when you're doing something that can be unsafe. If you really want to be safe, don't ever use multithreading, and that's extremely common. Multi-core CPUs became a thing, and were a very big thing, but even now, now it's changing. Games have multiple threads, and so, 6-core CPUs are pretty good for them. But for the longest time, if you would ask somebody, if I'm doing video editing, if I'm doing graphics, if I'm doing AI or whatever, get the computer with the most cores so you can do the most things at once. Oh, I'm playing games. Get the fastest Intel with 2 cores or maybe 4. And that was the key. Single core performance. How fast can you do something? Because the more cores, the slower it is. But it's 4 times 4 or 3 times 16. 3 times 16 is bigger. So if you're using all 16, that's faster. Only if you're using all 16. This is a topic for another time, but the point is, this is exactly why. Because multi-threading is hard and difficult and screws up all the time if you're not careful, and if you're careful, it can be slow. Careful is slow. So games programmers were screw it. They'll buy gaming CPUs. I ain't got to worry about it. But nowadays, it's getting better. It's been better for a little bit. Low core count is still king for games, but I bet VR changes the picture. But anyway, that's multi-threading. That's everything you ever need to know about multi-threading to be careful. If you want to do fun stuff like lockless programming, we may get into it more in the future, but I recommend looking up tried and true lockless algorithms. The only ones I really ever use are for status or for basically producer-consumer. I could create an object, memory barrier, and give it, and that's easy because it's all atomic. Or if I have a thread that counts how many times it does something, and then another thread wants to read that value and then display it once per second. I can do that, and you don't need to do any synchronization because it's a one-way flow. This one only writes, this one only reads, and they're atomic. So you can do safe stuff, but I recommend being careful, and you can be fast when you're better. So while you hit the gas pedal, I'll be seeing you.